types of aqueous solutions. So we talked about salt water. You can take a cup of water, add some salt, stir it up, you make a solution of salt in water. You can do the same thing with sugar. Teaspoon of sugar and water, stir them up. Both of those substances seem to disappear, but we know that they're still in there because you taste the water and you can tell they're there. How does a solid dissolve in water? What is going on that causes it to do that? Well, there are forces of attraction. We'll learn about what they are later. For now, we're just going to call them attractive forces. There are forces of attraction between the solvent particles and the solute particles. There are attractions between the solute particles, and there are also attractions between the solvent particles. So why does a glass of water stay a glass of water? Why does the water stay in the bottom of the glass? Why doesn't it float away and become a gas? Because the water molecules are attracted to each other. They're really tight with each other, and they're just going to hang out together as a group. Why does sodium and chloride, in sodium chloride table salt, why does it stay together as a solid instead of being a liquid or a gas? Because there's this force of attraction between the particles, right? So when we put these two different substances together, we now have the potential for attractive forces between the water and the sodium ions, between the water and the chloride ions. And what decides whether this is going to dissolve or not is the relative strengths of the interactions between the solvent and the solute particles compared to each substance with itself. Because not all ionic substances dissolve in water. So how do these attractive forces arise? So water, we just have to talk about water because water is everywhere, and it's really important. So here's an illustration, a space-filling model of a water molecule. So there's the oxygen and there's two hydrogens. This bond between an oxygen and a hydrogen, they're sharing electrons, but they're not sharing the electrons equally, right? You can share, you can share a bed with your spouse, but does that mean you each have exactly half the bed? No, typically one person has 2/3 of the bed and the other person's sleeping on the edge, right? Yeah, we're sharing a bed. Is it equal? No. Same thing with the covers, right? So here, the electrons are not being shared equally. The oxygen hogs the electrons. It's hogging the blankets. And so the oxygen has a slightly negative charge and the hydrogen has a slightly positive charge. And it does the same thing with the other hydrogen. So the oxygen is grabbing the electrons. It is not forming ions. They are still sharing. Forming ions would be one person gets kicked out on the floor and the other person has the bed all to themselves. They're still sharing, but it's not even. So we use this letter. This is a Greek letter delta, lowercase delta. It looks like the letter D with a posture issue. So here we have delta minus and delta plus, and we use those to indicate a partial positive and partial negative charge. This isn't +1 and -1, it's some fraction of that. We don't care exactly what. It might be 1/10 of a charge. It's a partial charge. So any questions on that? So the oxygen end of the water molecule is slightly negative, and the hydrogen end is slightly positive. So we put sodium chloride in water. Sodium chloride has positive ions and negative ions. The positive sodium ion is going to be attracted to this slightly negative end of the water molecule. The chloride ion is going to be attracted to the slightly positive end of the water molecule. And so now the sodium and the chloride have to decide, am I more attracted to this other ion I came in with, or hey, that water's looking pretty nice, right? What happens is a bunch of water molecules will surround this cation, putting their negative ends towards the cation. There's this attractive force between the opposite charges. and they will make this ion feel comfortable because charges do not like to be separated from each other. So you can't just pull sodium away from chloride and have it be happy. It's like magnets. If you just pull it away a little bit and it's still close enough, it's just going to stick back together again. So what happens is the sodium ion will go off surrounded by a bunch of water molecules. We say it's solvated. And the chloride ion comes over here, and it's being surrounded by water molecules, but they're showing it's the other side, right? So water's kind of a two-faced friend. It's positive and negative. One side is different than the other. Now these ions are free to move throughout the solution, sort of, carried around by these water molecules. So we have ionic charges, charged particles that are free to move. Charged particles that can move can carry electricity. So if we take a cup of pure water and we hook it up to this conductivity apparatus, here we have a battery. It's more exciting if you plug it into the wall. And you've got an electrode that comes in here and another electrode. They're not touching, but they're both in the same water solution. And then you've got a light bulb in here. When you have pure water, the light bulb does not light up because electricity has to flow in a continuous circuit in order for the light bulb to glow. And it can't get through the water. If we add salt, table salt to this, then the light bulb goes on. Didn't change anything else, just put some table salt in there, the light bulb goes on. Because as the salt dissolves, the ions separate. We've got mobile sodium ions and mobile chloride ions, and they can move and conduct the electricity, and so electricity can flow. So we call this type of a solution an electrolyte because it carries electricity. So electrolytes are substances that dissolve in water, forming solutions that conduct electricity. They are typically ionic solids that are soluble in water. So you may have heard about electrolytes in terms of sports, right? We had the Super Bowl, and they go out there and exert themselves and sweat a lot, and you need to replenish your electrolytes, right? So they're trying to sell you Gatorade. What does Gatorade have in it that's so special? Well, it's got some salts in it. Not just table salt, but some other salts as well, because your body needs those. And so when you sweat them all out, then you need to replenish them. A non-electrolyte solution does not conduct electricity. If we do the same thing and we add sugar to the water, you look at them, sugar and salt look pretty similar, right? They taste really different, but they look very similar. You add sugar to the water, the sugar dissolves, but the light bulb does not go on. Because sugar does not form ions in solution. It's a molecular compound, and it will not conduct electricity when dissolved. So it's a non-electrolyte. Any questions? Here we've got illustration of what's going on with the sugar. The sugar dissolves. The sugar has oxygens and hydrogens on its surface, and those are also not sharing equally. And so the water molecules will come and surround this and cause the sugar molecules to be moving around. But the sugar molecule doesn't have a charge on it, so it's not going to conduct electricity. Oops. So we learned a bit about acids. Acids are molecular compounds, but they ionize when they dissolve in water to form hydrogen ions. Right? That was our definition of an acid. Dissolves in water to form hydrogen ions. So the hydrogen ion is a cation, and the rest of the acid molecule becomes the anion. So those molecules essentially are pulled apart by their attraction for water. The hydrogen is very attracted to the oxygen end of the water. He's like, I want to go over here. And here the acetate is very attracted to the hydrogen end of the water. No, I want to go over here. And their attraction for the water pulls them apart, literally. They're pulled apart. So we have strong acids and weak acids. A strong acid will ionize completely. You put HCl in water, all of it ionizes. But most acids will only ionize a little bit. And so these are called weak acids. Only a small percentage of the molecules ionize. Most of them remain as molecules. So we see in this picture, this is acetic acid. It's a weak acid. Some of it will ionize. It'll form hydrogen ions, but a lot of it just remains intact hydrogen acetate molecules. HF is another example of a weak acid. We've got intact hydrogen fluoride molecules along with some hydrogen ions and some fluoride ions. So you could think of it this way. In a weak acid, the hydrogen and the fluorine have a stronger bond, a stronger attraction to each other than in a strong acid. So that kind of seems opposite. In a strong acid, these guys are willing to go their separate ways. Maybe you could say they have strong individual personalities. They're very independent, right? They're like, yeah, we can split up. We're fine. And these guys are weak, and they need to cling to each other and stick together. I don't know if that helps you remember it. So acids are electrolytes. Strong acids are strong electrolytes. Weak acids are weak electrolytes. So a strong electrolyte conducts electricity well. It conducts it strongly. The light bulb glows brightly. A weak electrolyte mostly dissolves its molecules, but does make some ions. And so it can conduct electricity, but that light bulb is just going to glow weakly. So a weak acid, a weak electrolyte, conducts weakly, with an A, not two E's. So pictures of the light bulb. So here we have a non-electrolyte. You put sugar in the water, light bulb doesn't light up at all. You put something like sodium chloride in the water, it's a strong electrolyte, light bulb glows brightly. Put a weak acid in here, a weak electrolyte. Come on, pointer. Come on. No? Okay. Having connection issues. Anyway, the one in the middle, the light bulb isn't as bright because the acetic acid only dissociates a little bit. So there aren't as many ions. There we go. There aren't as many ions. I don't know. Like this. There aren't as many ions in that solution. So the electric current can't flow as well. Any questions? I want to know what's up with my pointer. When we have an ionic compound that dissolves in water, we already had ions. They're just separating from each other. So this is called dissociation. Association would be things coming together. Dissociation is things going apart. There were ions already, and now they're just dissociating from each other. A molecular compound like an acid that now forms ions where there weren't ions before, we say that's ionization. It's the forming of ions. But here it's just dissociating. If we have polyatomic ions, those polyatomic ions stay intact. So we learned to name this as sodium sulfate. There's two ions. There's the sodium ion and the sulfate ion. And when that dissociates, we still have sodium ion and sulfate ion. There's only two kinds of ions. Okay? Na2 here just means that there's two sodium ions. Not that it's an Na2 2+ ion or something funky like that. It's just how many there are. So we've got the sodium ions and the sulfate ions. Polyatomic ions stay together. So which ionic compounds are going to dissolve? Because they don't all dissolve. Some of them will, some of them won't. We say a compound is soluble if it dissolves in water. We say it's insoluble if it does not. Well, it's not exactly black and white. There's kind of a gray area in between, because even insoluble compounds dissolve a teeny tiny bit. But overall, does most of it dissolve or not? If we take silver nitrate and add it to water, it dissolves very nicely. We have separate silver ions and nitrate ions. These are going to be surrounded by water molecules that make them feel comfortable. If we take silver chloride and put it in water and stir it up, it's just going to sit at the bottom. much like sand would, right? You put sand in water and stir it up, it's not going to dissolve. You let it sit, it's all at the bottom. Silver chloride is almost completely insoluble in water. So how do we know which one dissolves and which one doesn't? It's a little bit complicated. There's lots of factors. There's no easy way to predict it. So we use an empirical method. So scientists have taken different ionic compounds and they've tried dissolving them in water. Say, well, how much of this one will dissolve? How much of that one will dissolve? At what temperature? And a whole bunch of studies have been done. And all of this information is tabulated, and you can find it in the CRC, the giant book we have somewhere over there. Oh, it's over here now. It moved. Should put the lemming on the CRC. And so then they looked at this list of things and looked for patterns. And so we've got a set of what are called rules for solubility. Here they are. This doesn't cover everything, but this is what you need to know for Chem 1A. So I wish I could hide these because they sometimes cause more trouble than maybe they're helpful. You've seen the yellow cards, right, with the periodic table on one side and the conversion factors on the other side. We also have green cards that have a bunch of ion names on one side and solubility rules and a list of strong acids on the other side. Ooh, there it is. It'll stay there. The list of rules in there is slightly different than this one. And if you look online, you can find even slightly different rules. It's because it's not black and white. It's how is it defined. So answering mastering chemistry questions, go with this one, okay? And I want you to memorize this, okay? It's actually not that bad. So how does this work? The top half of the table is showing us compounds that are generally soluble. So if it has one of these ions in it, it's going to be soluble, except, oh wait, there's no exceptions. So there's some exceptions listed over here, but in general, anything containing these ions are going to be soluble. So what are these ions? Lithium, sodium, and potassium, those are group 1 metals, and ammonium. And so if you see one of those in the compound, it's going to be soluble. You don't have to look at the rest of the table. This table works best if you start at the top and work your way down. So if you've got nitrate ion or acetate ion, it's a soluble compound, no exceptions. Chloride, bromide, iodide, the halide sisters. Those are soluble except with these three. Let's see. So I think it's actually helpful to just get rid of a lot of these words so they muddy it up. Those are the exceptions. If you have silver, mercury, or lead with chloride, bromide, or iodide, it's not going to be soluble. So there's that silver chloride that we saw. Sulfate compounds are also generally soluble, except we have strontium, barium, lead, silver, and calcium. Well, what do strontium, barium, and calcium have in common? They're group 2 metals. And then here we have lead and silver. Those are the same things that we saw up here as exceptions. So those are the ones that are soluble with a few exceptions. The bottom one, these are compounds that are generally insoluble, and then we're listing the exceptions that are soluble. So if it's got hydroxide or sulfide, it's probably going to be insoluble except, so this first one, if you've got one of those ions with lithium, sodium, potassium, or ammonium, well, that got covered by this first rule up here. If you go down the table and you've got, say, sodium hydroxide, you're going to come up here, sodium with hydroxide, no exception, soluble. You're not even going to get down here, right? So we don't really need that one. because we're just going to go top down through this table. So we don't need that one. That simplifies things. So what's next here? Sulfur with calcium, strontium, or barium. Hydroxide with calcium, strontium, or barium. Why did they list those separately? Well, there's a teeny tiny difference. The sulfide ones are soluble. The hydroxide ones are slightly soluble. Slightly soluble. But for most purposes, we can just do that. We don't need that. Is that looking a little simpler to remember? These three with hydroxide and sulfide are soluble or slightly soluble. Up here, it was those same three that were insoluble with the sulfate. So it's that same three group of metals. And then down here, carbonate and phosphate. Again, we've got this, well, if they're with one of those, then they're soluble. Well, of course they are, because those things are soluble with no exceptions, so we really don't need that in there at all either. I guess we don't even need this word. Does that look a little better? Yeah. So we got rid of all the little details that are hard to look at. So you're going to need to predict whether things are soluble or not. So I would encourage you to have a short list like this, maybe on an index card. Let's see, I'm going to take a screenshot of this too. Wait a minute, there we go. Did it work? There it goes. Okay. So I took a screenshot. When you're doing these problems, try to think through the list and do it without looking at it, at the rules, and then check yourself. And that way you'll get practice and you'll kind of remember it without having to work at it too hard. So, predicting. Predict whether each compound is soluble or insoluble. Okay, so hit this one. We're going to look at this cation first. We've got nickel, and then we've got sulfide. And so we're going to go through the list. So we'll go back here. We'll go through the list and see if we see any of these ions in here. We're looking for nickel and sulfide. And we're not seeing anything until, oh, here's sulfide. Sulfide's generally insoluble except with calcium, strontium, and barium. Well, nickel's not one of those, right? Oh, I just got lost. So is nickel sulfide soluble or insoluble? It's insoluble. I'm writing with a white pen. That doesn't work very well. So that one's insoluble. Magnesium phosphate. So we go down the list. You see magnesium? No, no, no. Phosphate. Not soluble. So this is also insoluble. Lithium carbonate. We're not going to look at the list. Soluble. Because what's first on the list? Those alkali metals and ammonium. We don't have to look any further. This one is going to be soluble. As far as Chem 1A is concerned, there are no lithium compounds that are insoluble. How about ammonium chloride? Soluble. That's also one of those first ones that's soluble with no exceptions. To kind of get the idea of how that works? I'll take that as a yes.